All right, welcome everybody to chapter 21, integration. Integral calculus is the second half of the calculus coin. Um Differential calculus was all about graphically the slope of a tangent line and contextually the rate of change. Integral calculus, we'll see, graphically is about the area in between two curves, and contextually I like to think of it as being about accumulation of something. Think about that in terms of something we've studied already, kinematics. So we start with a displacement function, and when we take the derivative of it, we end up finding the rate of change of position over time, the velocity. So when we do this in the opposite direction, we start off with a velocity function, and what we end up getting is a displacement, which is an accumulation of position over a period of time. And you could extend this really to anything. If you knew that you were capable of eating so many hot dogs per minute and you had a function for that, we could reverse that. We could integrate that function to work out how many hot dogs you were able to eat in a particular period of time. And just to illustrate this with a really simple example, let's say we had an object that was moving with constant velocity. Now, since we know that distance is equal to rate multiplied by time, then we can easily answer this question of how far the object traveled by just taking its rate and then multiplying that by the amount of time it traveled for, and we get a distance of 40 centimeters. Now, visually, where this connects to like calculus and graphs is over here we've got a time elapsing of 0.2 seconds, and we've got a constant velocity up here of 200. And if we think about the area of that rectangle, it's also equal to 40. So that's the graphical representation here. How much distance or displacement did the object accumulate? 40 centimeters worth, and that connects with the area underneath its velocity graph. Now, this doesn't really work out if the velocity is not constant. Like, how would we calculate the area underneath this curve? Well, this is where calculus comes into play. And I don't want to spend a lot of time on this point because it's not something that is going to show up in the core. We will spend time talking about infinite rectangles in the option topic, but I will give you like a brief overview right now. This is a much more important topic in AP Calc than it is in IB Core Calculus. Okay, so to illustrate this point, let's say we have this quartic function. Here's what the function is if you're interested, although that's irrelevant at the time being. And we're interested, for whatever reason, in working out what is the area below this curve, but above the x-axis, and let's say in between -1 and 0 for now. Well, we have no way to directly calculate this based on elementary geometric shapes. But what we can do is estimate it. One could imagine drawing a whole bunch of little tiny squares and filling in this area and then counting up how many squares there are at using that as an estimate for the area. Perhaps you've done something like that back in elementary school. Really, we're going to use a very similar approach here. Instead of squares, however, we're going to use rectangles. Now, I'm going to walk you through a few different ways that one could do this. So here's one way that kind of arbitrary, but let's say we decided to start by looking over here at the left end point. And we said, hey, let's figure out where that left end point intersects the graph. So we set x equal to -1, work out what the y value is of that intersection point. We're just going to draw a rectangle in right there. In fact, here is that, here's that rectangle. We could work out the area of that rectangle. It's got a base of 1, and its height is whatever that y value is when we put -1 in there. Base times height, we've got an area for a rectangle. That's not a very good area estimate for the full thing, but it's a place to start. We could make this estimate better though. Instead of drawing one rectangle, we could draw two rectangles. Let's again start at the left, and we'll go up to where the left endpoint meets the graph, and then we'll just go halfway over. And then we'll go up again, so now we're at -1/2, right? We'll figure out where that meets the graph, and we'll make a second rectangle. So here's that second rectangle. Again, the base of each of these rectangles is 1/2, and I can calculate the heights pretty easily by just substituting in -1 and -1/2 into my function. Base times height, add them up, and I've got an area estimate. And visually we can tell that this area estimate is better than the previous one. And the more rectangles I use, the closer my estimate will be to the actual area. Of course, there's always going to be a little bit missing. So in this particular case, my estimates are going to be a little bit below the actual area. I could have done this a slightly different way. Instead of starting at the left, I could have started at the right. In this particular case, as I do more and more rectangles, I'm still getting closer to the real area, but I'm actually overcounting by just a little bit. And of course, there's a third way we could have approached this, and that is to use midpoints. For each rectangle, I could take the middle of the rectangle and figure out where it would intersect the graph. So here it is for 2. So my first rectangle would go from -1 to -1/2. I find the midpoint of that, that's -3/4, and I would work out where that intersects the curve. That would be the height of that particular rectangle. And the other rectangle would be at -1/4. Again, the idea is that the more rectangles we use, the closer the area becomes. Where this connects to calculus is as the limit, as the number of rectangles approaches infinity, is the true area, or expressed slightly differently, the limit as the width of each rectangle approaches 0 is equal to the true area. Now, whether we choose a what's called a left endpoint rectangle or a right endpoint rectangle, or sometimes these are called just left rectangles or lower rectangles, that doesn't necessarily mean that I'm necessarily underestimating or overestimating the area. As we can see, if we were to move this right boundary out here, whenever the function is increasing, a left rectangle will underestimate the area. However, when the function is decreasing, it overestimates the area. Likewise, when we take a right endpoint rectangle, it overestimates when the function increases, it underestimates when the function is decreasing, whereas that midpoint rectangle kind of does a little bit of both. And there's actually other ways to do it too. So on this screen, we're going to see actually 5 different rectangle types for the exact same function as before, and we're estimating the area in between -1 and 2 with 30 rectangles. So here's the left rectangle estimation that we just saw. It underestimates sometimes, it overestimates other times. Great. The true area is 6.6. Its estimation is 6.31. And down below, here's our right rectangles. Again, underestimates sometimes, overestimates other times. And there are other ways you could do it. Over here we have something called a lower rectangle. Whereas the left and right rectangles always intersect the graph at one of the endpoints, either the left or right endpoint, the lower rectangle just has to stay below the graph. So in theory, you could have the intersection with the rectangle and the graph be just somewhere in between the 2 endpoints. That's going to always underestimate. And here we have an always overestimating method with upper rectangles. Again, the graph could touch those rectangles anywhere, but they must always be above the curve. And here's our midpoint again. And we can see that the midpoint is certainly the most accurate method, but there are many rectangular approximations that one might try. You could also draw trapezoids. So the trapezoidal approximation method, they do that in AP Calc. There's something else called Simpson's rule, which gets you a very good approximation as well. What we're concerned with in this course is, again, in the core, not very much, but in the option, we'll deal with primarily upper and lower rectangles. So that's the connection between this idea of areas and calculus. I've presented it to you. I can sleep at night. That being said, we're not going to do any of these limits. With differentiation, we started with limits, and then we saw first principles differentiation, and that was an explicit connection between limits and derivatives. We will not have that explicit connection here for integrals. We're just going to do it. So let's do it. And here it is. Here's our new notation. If we want to find the area underneath a particular curve, f of x, in between two boundary points, we'll call it a and b, we can write this mathematically like this. We've got kind of an elongated s. That's the integral symbol. The number that goes on the left in the picture, that ends up down at the bottom, and the number that's on the right in the picture goes up top. We always include dx at the end of an integral. So the integral s thingy and the dx, they go together. You should never write one without the other. Well, you can write a dx if you're doing differentiation, of course, but you should never write the integral s symbol without a dx. Just like with derivatives, that tells us what the variable is that we were differentiating with respect to. It's going to be the same rules here with integration. We need to know what variable we should be interested in there. And in our course, we see implicit differentiation, where we had to take the derivatives with things with both x's and y's. We really won't be dealing with that problem with integration. We'll see a little bit of that with what's called differential equations in the option topic. But for the most part, we're not going to get too deep into this. There is such a thing later on, and for like further calculus, maybe you'll take in college, where you can start taking like multiple integrals, where you're integrating functions with respect to x and y, but we're not doing any of that nonsense. Okay, so first, if you see a problem with elementary shapes, you can evaluate something like this just by thinking in terms of geometry. They want to know what's the area in between 0 and 2 underneath this line but above the x-axis. So we could draw it, even if the picture here wasn't available to us yet, we could easily draw that on our own, and we'd see, oh, hey, that's really just a trapezoid there. So let's figure out the area of that trapezoid. You could either use your trapezoid formula, or you could break this into a rectangle and a triangle, but you could calculate those two areas, and that's the area underneath the curve. Same thing with the one below. We want in between 0 and 1 underneath this function. So we'd graph that from -1 to 1. That gives us actually a semicircle. So we're really just dealing with a quarter of a circle here with a radius of 1. So we can easily work out the area for that. Soon we'll be able to work out what those are algebraically using proper calculus, but you can answer questions without even without even knowing what the function is. If you have a weird picture with geometry in it, you can work out what the area is, and the question might be expressed using an integral symbol. One thing that's important to note about this, so far I've been describing area below a curve but above the x-axis. Of course, the curve might be below the x-axis too. We consider this area to be negative. So it's this idea of signed area, and generally speaking, negative area doesn't exist, but now it really has to for a lot of our applications to make any sense. Thinking back to the velocity example, you could think of, if this was a velocity over time graph, here an object might be moving forward because it has positive velocity, so it's accumulating a positive displacement, but then it starts driving or traveling, whatever, in the opposite direction. So it's accumulating a negative displacement. All right, we wouldn't add them together. 1 has to be negative. So we can work with that here. Again, just geometrically, we want to know the area in between 0 and 5. Let's say instead of under that line, let's say between that line and the x-axis. So we might figure out, where does that line cross the x-axis? It's clearly going to be at x equals 3. So the area to the left of that's going to be positive, so we'd work out that area. The area to the right of it is going to be negative. We'll work out that area. It ends up being 9 over 2 and 2. Do the subtraction. We get our final answer. For something with an absolute value, of course, absolute value can't be negative. So both areas are going to end up being positive now. Instead of subtracting 2, we just end up adding it. Okay, I feel like I've already used this word a bunch in this video. Integration is the process that we're describing here. It's the reverse of taking the derivative. It's also called anti-differentiation, which makes a little bit more sense, but it's far more syllables to speak, so that's why we prefer integration. Oftentimes, just for notation, we'll tend to use the capital letter F to be the integral of little f. So find the antiderivative of these three. Basically, we're asking what function, if I were to take its derivative, would have these as the answers. Take a look at the first two together. I mean, we know that the derivative of x to the fourth is 4x cubed, but that's not the answer that we want. We wanted just 1x cubed. So we divide both sides by 4. And we could work out, therefore, that the antiderivative of x cubed is 1/4 x to the fourth. And then we could go about the same process with e to the 2x. We know that the derivative of e to the 2x is 2 times e to the 2x, but we want to get rid of that factor of 2, so we divide both sides by 2. And then we get a final answer here. And the third one, perhaps a little bit more challenging, we're going to want to rewrite with exponents. So that's the function that we want the antiderivative of. We might be clever enough to recall, hey, if I take the derivative of x to the positive 1/2, that gets me 1/2 times x to the negative 1/2. So that means that we just want to multiply both sides by 2. So 2 times the square root of x is our antiderivative of 1 over the square root of x. There's kind of two big problems with this method. The first is, so you can tell there's kind of like a lot of guessing and checking happening here. Like I need to be smart enough to figure out what other function should I have used. Like sometimes that connection's not obvious. And secondly, some of you might already be picking this out. This is not, for example, the only answer, because if we started with 1/4 of x to the fourth, let's say plus 2, and took its derivative, the 2 is going to go away. In fact, if that were any constant, it would have gone away. We'll address both of these issues formally in the next video, but for now, just suffice to say, generally, when we're finding an antiderivative, we do write plus c at the end to indicate that there could be any arbitrarily chosen constant. But more about that in the next video, because we're going to finish this one up by speaking about something that does not require the plus c, which is definite integration. Definite integration simply means that we have definite endpoints that we're integrating between. This is kind of what we started talking about at the beginning of the video. We can evaluate a definite integral simply by finding the antiderivative of the function that we're given, and then evaluating that antiderivative at both the upper limit of integration and at the lower limit of integration, and just subtracting one from the other, always doing the upper limit minus the lower limit. This is something called the fundamental theorem of calculus, or at least this is part of the fundamental theorem of calculus. We're going to expand on this idea a lot in the next video, so don't worry much about this. For now, just there it is. The book introduced it in this section, so I mentioned it, but there's more to come, I promise. Finally, we close off with just some general properties of definite integrals. And let's just think about these in terms of areas. So this first one, the integral from a to a, that's always going to be equal to 0. Now, you could think of that partially because according to the fundamental theorem of calculus, this is going to be big F of A minus big F of A, so clearly that's going to be equal to 0. But you could also think of it as we're finding the area underneath a curve in between two values that are really the same thing. So it's an infinitely narrow area. There truly is no area to be found. Second one, down below it. Notice that when we change the limits of integration, when we just reverse them, our integral becomes negative. So the area in between B and A is equal to the negative of the area in between A and B. You can kind of justify this a little bit by thinking again about kinematics. The total distance accumulated by an object traveling from time 1 to time 2. Well, if we reverse the two times, I don't know, like I guess you could imagine that as watching the object move in reverse time. It's clearly going to be displaced in the opposite direction. Third bullet point, if we take two definite integrals and add them together, as long as the upper bound of one matches with the lower bound of the next, we can just combine those two into a single integral from the original lower bound to the second upper bound. And graphically, I think that makes sense. We're just taking two areas that match up at one endpoint and putting them together. But also algebraically, that makes sense since we're getting big F of A minus big F of B minus little f of A plus big F of C minus little f of B. Of course, the b's will cancel, and we're left with big F of C minus big F of A, which is precisely what we get from there. Next, just like with derivatives, if we have two functions that are being added or subtracted, we can integrate them both separately and then add or subtract the results. Okay, that one I think is pretty straightforward. On the top right, this one's perhaps a little weird. So this is the integral of a constant. Should be equal to that same constant times b minus a. Now this is, again, graphically, this is exactly what we started with that object that was traveling at a constant velocity over a period of time. That constant velocity would be the rate, and then the amount of time that had passed, that's our b minus a here. In the example given before, we had 0.2 seconds, I think, because it was between 0.1 and 0.3. 0.3 minus 0.1 is 0.2. So you can kind of see that. Later on, when we understand how to actually take antiderivatives, you'll see why this rule is also true there. And then finally, this last one also reminds me of derivatives. If we have a constant times a function and we want to take the integral of the whole thing, we can just take that constant out, we can factor it out, and then just take the integral of what's left over. Again, our integral is interested in that variable x. So if there's a factor that has nothing to do with x, we can take it out. Okay, this video is purely like foundational. There's actually not a lot of interesting calculus to be found here. We're going to get into that in the next one. We haven't discussed at all how to actually calculate integrals. You are right to feel frustrated by that, but sorry, we'll get there very soon. For right now, it's just connecting this idea to areas is the big idea that we need to be comfortable with, and then there's plenty of time to worry about how to calculate integrals and then figure out their further applications down the road. But until next time, that's it.